We present duplex Gaussian, a proxy-guided weighted blending method for real-time order-independent Gaussian splotting. Current 3D Gaussian splotting achieves real-time performance through sequential alpha blending, involving tiling, replication, sorting, and blending. Early termination is easily implemented once the alpha is saturated, but this approach introduces popping artifacts due to sudden changes in local Gaussians. Moreover, sorting such long sequences is inefficient for hardware like GPU graphics pipeline, FPGA and ASIC implementations. Sort-free Gaussian splotting offers a novel rendering method, inspired by weighted sum order-independent transparency. It uses a function that decreases with Gaussian depth to simulate original transmittance. However, the lack of a front-to-back order complicates termination, which slows rendering and introduces transparency artifacts. Our goal is to design an algorithm with minimal sorting and high parallelism potential, suitable for resource-constrained platforms. We begin by revisiting the neural anchor, which encodes Gaussian clusters with a point. However, Gaussians can deviate significantly from the anchor, which is hard to utilize for accelerating rendering. We introduce a neural cell that encodes local Gaussians using an ellipsoid proxy, which constrains the Gaussians within a cell. With these novel cell proxies, we create a dual-layered hierarchy. In the first layer, rasterization is done using cell primitives, with sorting based on cell sequence. Since the number of cells is much smaller than that of Gaussians, this sorting is lightweight. The activated cell is then decoded to Gaussians through a small MLP. In the second layer, we perform weighted sum rendering cell by cell. Since Gaussians within a cell are unordered, blending is highly parallelizable, and early termination at the cell level speeds up rendering and removes transparency artifacts.